on the topic of the derivative of a function. The derivative of function f at value like a is the limit of the difference quotients if exists. So f prime at a is equal to the limit of f of a plus h minus f of a divided by h as h goes to 0. When this limit exists, we say that function f is differentiable at value a. An equivalent definition of the derivative can be also written this way. The derivative of f at a can be written as the limit of f of x minus f of a divided by x minus a as x goes to a. So basically, our goal is to find the rate of change of the function at a specific value. So our goal is to get to a tangent line at a value. As the distance between a and a plus h is getting smaller and smaller, this line, which passes through 2 points, is getting closer and closer to a line that passes through just one value. So it becomes a tangent line. So let us analyze different types of functions and find their derivatives. We begin by a constant function, f of x equals to k, or f of x equals to c. Then, first of all, the limit of f when x approaches any value is going to be that constant value k or c or anything that is representative of the constant value. A constant function has a flat graph. It means that it's just a line horizontal to x-axis. Compare these two limits. Here you have the limit of x. As x approaches 3, you just substitute 3 and you get 3 back. But if it's just a constant like 4, it doesn't matter where x goes to. The y value is constant and it's always 4. So here you have an example of a constant function, and the limit of constant function at any value is going to be that constant value of y. Remember that slope of the constant function is equal to 0. So the rate of change is equal to 0. That's how we can analyze the derivative of a constant function. F prime of x, as we defined, is the limit of f of x plus h minus f of x divided by h as h goes to 0. But since if you have a constant function like c or k, you can substitute this with any value. Divided by h, it becomes the limit of 0 or just 0. So the rate of change of constant function is always equal to 0, and basically you can see that the limit is equal, the slope is equal to 0 as you calculated the limit. So it's easy to find the derivative or rate of change of a constant function. You can say that in general, f prime of x is equal to 0 for all value of x in the domain, because this function is defined everywhere. Let's take a look at identity function. Identity function is defined as f of x equals to x, and it passes through the origin, basically a line with positive slope, which is 1, and as you can see, it is an increasing function. The domain of this function is negative infinity to positive infinity, with range negative infinity to positive infinity. If f is the identity function, f of x equals to x, then for any value of x sub 0, the limit of f of x as x goes to x sub 0 becomes x sub 0. So basically do a simple substitution. Now let us take a look at the derivative of this function. F prime of x is the limit of f of x plus h minus f of x divided by h. So wherever you see f of x plus h, you're going to substitute x plus h into the function, which results in x plus h, because x and y are the same. Minus f of x is also equals to x. So what happens? You can cancel out x and negative x. You get h divided by h, which is basically 1. The limit of constant function, as we saw, is always equal to that y value, which is in this case 1. So the rate of change of identity function is equal to 1, you can also write down if f of x is equal to x, f prime of x is equal to 1 as well. Let's make it more interesting for you. If n is a positive integer, then the rate of change of x to the n is equal to n x to power n minus 1. For example, consider f of x to be x to the n, and then f of x plus h becomes x plus h to power n. Now, we can use basically the binomial theorem to expand x plus h to power n. F prime of x, which is defined as the limit of f of x plus h minus f of x divided by h as h goes to 0, is the limit of x plus h to power n minus x to the n. This is basically what we have for f of x plus h. Wherever you see x, you substitute that by x plus h into this function minus f of x, which is basically x to the n. Now let us expand this guy. You get the limit of x plus h to power n is x to the n plus n, x to power n minus 1 times h, plus n times n minus 1 divided by 2, x to power n minus 2 times h to power 2, plus the rest of the terms, plus n, x, h to power n minus 1 plus h to the n, minus, we're going to copy down whatever is left. Later on, we're going to simplify this and divide everything by h. This can be written as you can see, x to the n and negative x to the n, they get canceled out. So you're left with n, x to power n minus 1 h plus n times n minus 1 divided by 2, x to n minus 2, h to the second power plus the rest of the terms. But please note that all of these terms, they have h in common. So if you factor out h and simplify this further, you get n times x to power n minus 1 plus n times n minus 1 divided by 2, x to power n minus 2h plus the rest of the terms. But note that we are taking the limit as h goes to 0. So when h goes to 0, all of these terms that have h in them becomes 0. So you end up with n times x to power n minus 1. So here's a proof for you. Now let's take a look at a few examples. We just saw that the rate of change of x to the n as a power function is n x to power n minus 1. Consider some f and their derivatives. If f is equal to identity function, the derivative becomes 1. If f is x to the second power, its derivative is 2x to power 2 minus 1, or 2 times x. If you have x to the third, the derivative becomes 3x squared. If you have x to the fourth, the derivative becomes 4x cubed. You can continue this process. Let me show you how to basically use the definition, limit definition of derivative, and find the derivative of x to power 4. F prime of x is basically the limit of f of x plus h minus f of x divided by h. So wherever we see x, we're going to substitute that by x plus h. So wherever you see x, we're going to write x plus h. It has exponent 4. Okay, copy this guy down. Minus f of x, which is x to the 4, divided by h. Now let us expand this. This becomes the limit of the expansion of x plus h to power 4 is this quantity here. You have x to the 4 plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. You're going to copy down x to the 4th here and simplify as much as you can. As you can see, x to the 4th and negative x to the 4th, they get canceled out. So you're left with 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th divided by h as h goes to 0. So please note that all of these terms, they have h in common. If you factor out h, you end up with 4x cubed plus 6x squared h plus 4x h squared plus h to the 3rd. But since h goes to 0, all of these terms disappear and you simply get your 4x cubed back, which is exactly the same as the shortcut for x to power 4 minus 1, or 4 times x to the 3rd. We have other scenarios. If you multiply x to the n by a constant, like coefficient c, it becomes c times n to power x minus 1. For example, if you take the derivative of 3x to the second, it becomes 3. So 3 stays the same. The derivative of x squared is 2x. 3 times 2 becomes 6 times x. Let us compute more interesting functions. For example, if you have square root of x, what is the derivative of square root of x? Let us use the limit definition. By using the limit definition, here we have the square root of x plus h minus square root of x divided by h as h goes to 0. Multiply the numerator and the denominator by the conjugate of the numerator, which is square root of x plus h plus square root of x. If you simplify this further, it means that you're multiplying these terms together. So, and you get rid of the opposite terms, and you get 1 divided by square root of x plus h plus square root of x. And when h goes to 0, this becomes 1 over square root of x plus square root of x, or 1 divided by 2 times square root of x. So this is following the exact definition of the derivative. We can apply the shortcut as well. For example, if you have 1 over x squared from algebra, if x squared is on the denominator, you can write it on the numerator with negative exponent. So this becomes the rate of change of x to power negative 2, which is negative 2 times x to power negative 2 minus 1, or negative 2 x to power negative 3, or negative 2 divided by x to the third. Now, if you have a function like this, the third root of x squared, simply, if you have the third root of x to the second, you can write it as x to power 2 divided by 3. Then you can apply the rule that we just explained. This becomes the rate of change of x to power 2/3, or 2/3 x to power 2 over 3 minus 1. This becomes 2/3 x to power negative 1/3. So that's how we can use these shortcuts to find the derivatives of functions with different exponents and power functions.